All right, awesome. Welcome everyone to the November version of the Ice Giant Systems seminar series. We've got Will Saunders here, and I just want to mention that I believe next month we don't actually have a seminar scheduled, so we're just kind of taking a month off for the holidays, and as things hopefully kind of slow down a little bit over the holidays, and then we'll ramp back up in January. I believe we have Mark Hofstadter. You can check that link that I put in the chat. The homepage has all of the future talks that you can register for, and so feel free to go there to check that out. I believe it's Mark. And also, just as a heads up, over the next couple months, we're changing how we do registration for this seminar series, and so we don't intend to require registration in a couple months. So that'll be really helpful. It'll be easy to kind of share the link with your coworkers and colleagues and friends, and they won't have to kind of take the extra, couple minutes to register. So that'll be coming soon, and we're looking forward to that. So it'll hopefully make things a little bit more streamlined and get a bigger audience too. So I'll real quick introduce Will, and then I will hand it over to him. So Will Saunders is a fifth-year PhD candidate in the astronomy department at Boston University. He currently has the Future Investigators in NASA Earth and Space Science and Technology, or FINEST. I think some people pronounce it finest. I've always pronounced it finest. Fellowship and studies planetary atmospheres using stellar occultations. His dissertation is on the upper atmospheric temperature structures of Uranus and Neptune. Will has also previously studied gravity waves in the middle atmosphere of Mars using stellar occultations, and was involved in a concept study for a low Earth orbit spacecraft to observe stellar occultations by Uranus and Neptune. Outside of research, Will co-hosts the bi-weekly podcast Astro Soundbites, which is the audio counterpart to the popular astronomy blog Astrobites. He is currently on the hunt for postdoctoral positions with a flexible start date, and today he will discuss his current work on temperatures of Uranus's atmosphere. So go ahead and take it away, Will. And I'll turn my video off just so that I'm not distracting in the recording, but go for it. It's all yours.
All right. Thanks so much, Jody, for the introduction and for having me as a speaker today. And thanks everyone for joining. I'm excited to share with you what I've been working on for the past few months. All right, and good, we can advance the slides. So here's an outline on what I'm going to be talking about today. I'll begin with some background on Uranus and then offer some background on stellar occultations. I'll describe how I process my data, some of my primary findings, and then offer some conclusions at this preliminary stage. So we'll begin with the atmosphere of Uranus, and to go even further back than that, let's look at some comparative planetology. This is a really great plot that I love. Ingo Muller-Wodarg put this together for a 2008 review paper, and it compares all of the temperature profiles for all of the atmospheres in the solar system. And I'll trace out Uranus. It's in the brown line. So you can see in what might be the troposphere or the lower stratosphere, Uranus and Neptune are on top of each other. And then in this portion, Uranus has the coolest stratosphere of any atmosphere, then rapidly warms into a very hot thermosphere, the warmest of any of the atmospheres, and in the upper thermosphere maintains that trend among the warmest in the solar system. So compared to all the other atmospheres, Uranus does have some peculiarities right off the bat, both in the actual temperature as well as the thermal gradient we see in this plot. And on the right, I'm showing the comparison of the range of observed temperatures in the upper atmosphere of the giant planets compared to the temperatures expected from solar heating alone. And of course, this leads us to the giant planet energy crisis, this notion that the upper atmospheres of all the giant planets are far too warm to be explained by solar heating and other known sources of heat transport. Uranus has mysteries beyond the other giant planets, though, and some of these include the fact that Uranus and Neptune have the same effective temperature, the same tropospheric temperature, despite Neptune receiving less than half the insolation of Uranus. Uranus appears to have the warmest lower thermosphere of any planet, and yet also has the weakest internal heat source of the giant planets. So the three of these are clearly linked together, and yet stand in some amount of contrast. Uranus has weak vertical transport compared to the other giant planets, has the least visible cloud structures compared to the giant planets, and yet has a well-equilibrated stratosphere, despite the fact that for decades at a time, only one hemisphere of the planet receives sunlight. So certainly there are a lot of mysteries in just the neutral atmosphere of Uranus. I haven't even touched plasma stuff. And of course, this was recognized by the Decadal survey a decade ago, ranking a Uranus orbiter and probe the third flagship priority after Mars sample return and the Europa Clipper, both of which have been funded. And then in the most recent Decadal survey, of course, we all know Uranus orbiter and probe was ranked the #1 flagship priority. So I think we're all excited about this possibility. Certainly people at APL know about it well, being commissioned to do the concept study in advance of the Decadal survey. And I think we're all hoping for an early 2030s launch to deliver a heavy payload to the Uranian system. But long in advance of a mission to Uranus, and independent of those observations, there are ways of measuring vertical temperature structure of the neutral atmosphere of Uranus. Historically, there have been 3 methods. The first of which is Earth-based stellar occultations. This is what I do, and I'll spend most of the talk talking about this. And between 1977 and 1998, there were 16 occultation events. Some of them were observed multiple times, and each one has an ingress and an egress, which is how I get to the number 44. Second is Voyager 2 radio occultations. Radio occultations are considered some of the most reliable remote sensing measurements of a planetary atmosphere, but they're only sensitive to the lower atmosphere. And then third, the Voyager 2 UV stellar and solar occultations. These are sensitive to a huge range of the middle to upper atmosphere. However, one of the limitations of this method is that they're highly sensitive to the cross-section absorbing and scattering area of species in the atmosphere of interest. And as you can see in this plot from the Stevens 93 paper, these H2 bands are just represented with vertical lines because they're unresolved by the Voyager UVS instrument. And so in fact, Floyd Herbert in his 87 paper mentioned it very clearly that there's a lot of uncertainty in the way this processing was done because some of these bands were not so well understood. And then last, I include here the Spitzer infrared spectroscopy. I put it with question marks because I'm not quite sure if it's considered truly independent. If this is something you do or you're familiar with, reach out and I'd love to have a conversation so I can better understand how this fits into the picture. But certainly I'm intrigued by this work as well. So now let's take a look at these methods that I've talked about. And I'm showing here temperature versus pressure for Uranus, going to span the entirety of the atmosphere. And in the lower atmosphere, these are the radio occultations, which show a fairly cold troposphere into the lower stratosphere. Then I'll add on the Voyager UV occultations. So these run from the radio occultation region all the way up to the exobase. And what you can see is in the red and green dots, it's really 1, 2, 3, 4 points with an anchor in the radio occultations connected with line segments. And so in reality, there were only these 4 distinct measurements. And then Mike Stevens, a few years later, built what he called the one heat source model, which I put in here with the dotted lines to capture the behavior reflected in Floyd Herbert's 87 paper. And that has become sort of the representative atmosphere of Uranus, connecting the radio occultations to this very rapidly warming thermospheric profile. And then here are the Earth-based stellar occultations. And what you can see right away is there is some tension between these measurements. You see some tension in these points and then a great deal of tension with these points. And certainly nothing in the Earth-based occultations reflects the Stevens 93 models here. In addition, it's worth pointing out that none of these processings reported error bars. So it's hard to say how much trust we put in these 2 points, for example, or whether or not this thermal gradient is physically possible. If you recall this plot from a few slides ago, when I showed this rapidly warming thermosphere, that essentially was constructed from the radio occultations connected into this model and tends to be what people report as the textbook atmosphere of Uranus. Now, there are a lot of questions that can be asked from a plot like this. However, the ones that motivate my work are these. First, what is the upper atmospheric temperature of Uranus? And two, are reported Voyager 2 upper atmospheric temperatures consistent with Earth-based stellar occultation observations? So that's the background on the atmosphere of Uranus, leading to the questions that I'm interested in answering. And now I'll give you some background on stellar occultations, which is the method I've used to understand the atmosphere of Uranus. When I talk about stellar occultations, I always mean an Earth-based occultation, in which case a solar system body, Uranus in this case, is blocking a distant star. And it is the refraction of light through the atmosphere that creates the characteristic light curve. In fact, it's the differential refraction. And here I have a nice diagram that illustrates this well. So when light from the star passes far away from the planet, it passes through unobstructed, we receive it at full intensity. But as the light rays pass closer and closer, the previously tight bundle of rays becomes spread out as they bend more and more. That's the differential refraction. It's not the bending angle, it's the fact that the bending angle increases with time. And that creates this characteristic light curve, dimming the intensity down to a point where we can no longer see the star. And of course, the faster we measure this and the lower read noise we have, the more accurate information we can get about the atmosphere, the better vertical resolution we can have. Here's a nice animation I put together showing what it looks like to observe an Earth-based stellar occultation, where on the left, the aqua ball is representing Uranus with some thin layers of atmosphere around it, and the orange circle represents a distant star that'll pass behind the planet from this vantage point. So as the star passes behind the atmosphere, the differential refraction causes that light to decrease to zero. And normally there'd be something like a half hour in between here where the star is completely gone, but I've removed that piece. And then as the star returns, the light returns back to its pre-occultation flux. One important thing to note here, the star is unresolved. So unlike an exoplanet transit, it's not that the planet is blocking a portion of the stellar disk. It's that all of the starlight is being refracted through the atmosphere as a function of time. A few weeks ago, I had the pleasure of observing an occultation by Uranus using the IRTF. And this was the first one I've happened to observe where the data came out really good. So this is in the K band. What you can see is this is the body of Uranus. And then these are the rings, which are nearly face on at this point. And this is the occultation star. So I'll let this animation play. Being able to watch the star disappear and reappear in real time was incredibly cool. And at this stage, the light curve I've extracted from this occultation looks like this, which is pretty good. I'm not done with this. It's still in the early stages of processing, but I'm pretty excited to analyze it. And worth pointing out some nomenclature, we call the beginning of the occultation an ingress and the end an egress. When we consider the geometry of how an occultation works, one thing to note is the way the light rays pass through the atmosphere. So you can imagine a light ray passing through the outermost layer of Uranus's atmosphere tells us about that layer, but all subsequent light rays don't just pass through the close approach layer. They also pass through every layer above, both going in and coming out. So when we receive information about the ray, we're not receiving information about an individual layer of the atmosphere. It's actually a little more complicated than that. And so we have to solve an inverse problem here, where we receive information about the light rays, but what we really care about is the atmospheric properties. And those properties are number, density, pressure, and temperature, where temperature is really the thing I'm most interested in. So now I'll talk about how I do processing and analysis of stellar occultation observations. Before I mentioned the questions that motivate this work, what is the upper atmospheric temperature of Uranus? And to answer that question, I'll explain how I reprocessed archival ground-based stellar occultations. And then question 2, are reported Voyager 2 upper atmospheric temperatures consistent with Earth-based occultation observations? And for that, I'll explain how I used a forward modeling procedure to compare the Voyager data to the ground-based data. So some more detail on these methodologies. First, stellar occultation processing. We receive flux during the occultation, and then we convert that into a temperature profile as the end result. And this requires a two-step process, the first of which is finding a boundary condition. We do this by fitting a model to the overall light curve. That gets us a starting point, an anchor point at the upper part of the atmosphere, and then we solve the inverse problem, appropriately called inversion. We go point by point down the light curve, converting those into temperature, pressure, number density, and so on. Here's an example of how that might work. So in black is a light curve, a fairly high resolution, and in red is one of the atmospheric models we might use. So we fit the model to the data. That gets us an anchor point or boundary condition. And then where that arrow is, we would begin each individual point of flux, converting that into its own temperature, pressure, and number density. And then, of course, we can compare these temperature profiles to each other and to the published Voyager profiles. So that's method 1. Method 2 is what we call forward modeling. And it's essentially the opposite. Instead of putting in a flux and getting out a temperature, we actually put in a temperature and get out a flux. And the result of this is we're able to simulate what sort of light curves we would observe if the Voyager reported temperatures are correct for Uranus. And then we can compare the simulated light curve to observed light curves. So you can imagine that if the results of method 1 and method 2 disagree, one of the methods might be suspect. And this is a good independent check. However, if they both say the same thing, well, then we have 2 ways of getting to our answer. And that is a much more reliable approach in this way. So I want to explain a little more detail about how each of these processes work. And to do that, I'm going back to this nice diagram to show you some of the variables so you'll understand when I put them in context in the next slide. So we tend to call the close approach distance of each ray R, and we choose the letter Y to represent where that ray is received on Earth. And you can imagine then there's a bending angle between R and Y that would be 0, far away from where the occultation is, and then gets bigger and bigger. And once we calculate those thetas, we can calculate what we really care about, which is the d thetas. And then from there, we can calculate the way that the refraction would have affected the atmosphere. All right, so I'll put that in the upper right-hand corner, quickly move through a little flow chart on how this procedure works. We take in flux and the observer position, put them together, and we use Snell's law, assuming geometric optics holds, to find the close approach distance of each ray. From there, we use a small angle approximation and find that bending angle. Of course, then we have the differential bending angle. Then the most important step, we find the index of refraction. And this variable nu is the refractivity, which is index of refraction -1, basically the same quantity. The Abel transform requires some assumptions and is essentially that step in which we take the light ray picture and we convert it into the atmospheric picture. We take out all the contributions from each layer of the atmosphere in every individual light ray. From there, by assuming the atmosphere is homogeneous, we get the number density. Then we can use hydrostatic equilibrium and the ideal gas law to get temperature, pressure, and what we care most about, temperature versus pressure. There are a few important improvements in this method in the last few decades. First of which is the upper boundary condition is no longer an isothermal model. It's now a thermal gradient model, which is more realistic for the giant planets, especially if we're trying to test what the upper atmospheric temperature structure of Uranus is. To give you an example of how this works, here is one of the reprocessings that I've done. And the dotted line, or the dashed line, represents the results from using an isothermal model, and the solid line represents the newer thermal gradient model. So you can see these red points are the boundary condition. And so the model gets us the boundary condition. At that point, the model is still relevant, but it becomes very quickly swamped by the inversion point by point of all the data. So you can see there are very similar trends in the way these two models progress down, but the boundary conditions do change that starting point. So that is an important difference. Next, we have a higher vertical resolution than was possible decades ago. We don't need to bin our data to process it. And last, we can report error bars. So on the right here for the thermal gradient, you're seeing the 1 sigma error in the shaded region. Then the forward modeling procedure, as I said before, is very similar to inversion, but essentially the reverse, where we start with a temperature profile, taking the Voyager 2. We grab some of the Voyager 2 reference values that were published. We do hydrostatic equilibrium, ideal gas law, and we get to the index of refraction. At this point, we know where the observer was when the actual data was observed. So we can find the angles of each bent light ray corresponding to the refractivity. And that no longer requires an Abel transform. We can run things forward instead of backward. And our last result is, of course, the simulated occultation flux that we can compare to the actual observed flux and ask, are they consistent? I have a bunch of data that is available to me. I have some wonderful collaborators who have made archival stellar occultation observations available, 16 events, 6 of which had multiple observers, and each of which has an ingress and an egress, getting 44 potential profiles. If you're curious, I also have a lot of data on Neptune, not quite as much, but still plenty. I haven't yet processed all the data on Neptune, but that's in my future for sure. All right, so now let's get to some of the main findings. Here I'm showing an example of one of the inversion results. This one's from 1977, and a few things jump out right away. The first of which is the vertical resolution. You can see in here all sorts of small scale structures that were just unresolved in the original Jim Elliott processing. In addition, you can see the temperature at the top of these profiles disagree pretty strongly. And that's probably due in large part to the boundary conditions, but also possibly due to other improvements in the inversion procedure over time. In addition, we now have error bars. So in fact, the new processings lie completely outside, or the original lie completely outside the error bars of the new processing. So that's one. Here are all of the 10 that I've processed. Well, so 5, each of which has an ingress and an egress, so 10 profiles. A few things I want to point out here. At the top, all of these profiles lie within the overlapping error regions. I've only included errors for 4 of the 10 here, because otherwise it just gets too busy to see. So it's nice that they all sort of fall within the shaded regions. That's a good sanity check that our upper boundary conditions are reasonable. And in the bottom, interestingly, they all sort of converge around this point and stay reasonably well converged toward the bottom of the profiles. But in the middle, they disagree outside of the error bars. And I'm curious to see if this might be a diurnal variation, a seasonal or latitudinal. So this is something I hope to explore once I have all 44 reprocessed. But you can see there are interesting patterns, such as this temperature turnover here, and another one a little bit higher up. So even where they disagree in absolute temperature, they actually do have very similar features. Here is the same as the previous slide in context with the big temperature pressure profiles for the atmosphere of Uranus. And so I'll go back to the original processings and flash back to mine, put the original ones on the side so we can compare them at the same time. And there are a few major things that jump out from this plot. The first of which is this Floyd Herbert point here at 200 Kelvin, which seemed in stark contrast to these results, actually no longer looks so ridiculous. It's not quite within the meat of the reprocessing, but it no longer seems completely ridiculous. However, these 2 points still seem completely ridiculous, unfortunately. And the Stevens one heat source model doesn't agree any better with the reprocessed data than with the original data. We do see warmer temperatures in this region here, whereas these profiles stopped at about the 1 microbar pressure level. We can go a little bit higher, and we see that in fact the atmosphere does show a warming above that pressure level, indicative perhaps of the beginning point of the lower thermosphere, maybe being here instead of what might be called here or here. Here's a zoom in of the same plot, just so you can see that this point does lie outside of what we might take to be the median of the profiles, but it's probably within the error bars of this one in brown here. So as I said, it's not completely ridiculous. So to summarize from the first method I used, we might have actually relieved some of the tension in the original measurements. However, the bulk of the tension really remains with the upper Herbert points and with the entirety of the Stevens models. Unfortunately, those tensions prevail. Now for the forward modeling results. What I'm showing here is an example of one of the occultations that I worked with. This is the ingress profile of one of those. And instead of plotting versus time, I'm plotting versus the altitude above the 1 bar pressure, so I can compare everything on the same scale. These are the forward modeled light curves from the Voyager 2 models that Mike Stevens produced. When I first saw this, a few things jumped out to me right away, which is that in this region where there is atmospheric turbulence indicative of these spikes, it's really impossible to compare that to a smooth atmospheric profile. However, where the noise is approximately homoscedastic in the rest of the region, we can do a comparison. And these are what those residuals look like. So to my eye, it certainly looks like these residuals differ from 0 significantly. But that's not very scientific. So really what I wanted to answer is, are these residuals normally distributed? If they are normally distributed, then I can say, well, my eye was deceiving me. And in fact, these are not statistically significantly different. But if they are not normally distributed, then perhaps I could make that claim. And the forward modeling would represent that the Voyager results are in disagreement with Earth-based occultation measurements. So same plot here. One way of looking at this is by breaking the residuals into a number of different bins. Here I'm showing 5, but in fact I used 10 total going off to the right side of this plot. And here are the empirical distribution functions for those 10 different chunks. And we can play everyone's favorite childhood game, which one of these is not like the other. So if you guessed that one, you'd be correct. And indeed, that is the one chunk that corresponds to the occultation here. So it certainly passes the eye test, but again, it doesn't rise to a level of statistical rigor. So to apply that rigor, I used the Anderson-Darling test of normality. The Anderson-Darling test is a non-parametric statistical test, and it tells you whether or not data is drawn from a chosen distribution. In this case, I chose the normal distribution. So again, same plot as we've been looking at. And the way the Anderson-Darling test works is it gives you a statistic value at a confidence threshold. If your test value exceeds the confidence, then you can say it's non-normally distributed. However, if it falls below that critical level, then it is normally distributed. First thing I did was ran some baseline data. So I took data away from the occultation all the way out here and found it actually is normally distributed. That is, it fails the test of non-normality, compared to the occultation data, which far exceeds the critical value. Indeed, according to the Anderson-Darling test, these 3 residuals are highly non-normal. Therefore, we can say that the Earth-based occultation and the Voyager 2 models are in tension. If you're curious as to why I chose the Anderson-Darling test or have any more questions about this, feel free to ask, and I'm more than happy to elaborate. So from the forward modeling procedure, all of the profiles, I showed you one example, but all of them have the same pattern. They all exceed the 99% confidence threshold that the data is non-normally distributed. That is to say, the Stevens 93 models, which are based on Voyager 2 observations, are inconsistent with Earth-based stellar occultation light curves to a high degree of statistical confidence. I presented this work, or an earlier version of this, at the EPSC conference last month, and someone suggested trying to run my own results through the forward modeling to see if my own temperature pressure profiles do better than the Stevens ones. It'd certainly be disappointing if that were not the case. So in red is the result of forward modeling my own reprocessed light curves. That is to say, take my own temperature pressure profiles and simulate the light curve that I would get from them, and it does overlap with the actual light curve really well. You can see here, this is the region where we use the boundary condition, and then this is where inversion takes over and does all the little squiggly bits. And it's interesting, there's actually sort of a weird offset in altitude here, which is not that important, but it's something I'm definitely going to explore. But in the region of greatest interest, it overlaps really well. So I posed these questions from the beginning. I'll try to answer them now. What is the upper atmospheric temperature of Uranus? Well, it seems to be warmer than the original stellar occultations suggest, however, cooler than the Voyager 2 profiles. And I would say if the picture of a strong thermospheric heating on Uranus is correct, it likely begins higher up in the atmosphere, that it would not be consistent with the Earth-based occultations to begin as low as is claimed. And then, are the reported Voyager 2 upper atmospheric temperatures consistent with ground-based stellar occultation observations? No, for the Stevens 93 models, I can say that they are inconsistent. Some conclusions at this stage. Stellar occultations are a reliable method of measuring planetary atmospheres, and I would hope that as people build engineering models for studying the descent probes and other sorts of models, that these results are incorporated into other results. In addition, changing the picture of Uranus's lower thermosphere might change the way the energy crisis is understood. So I hope some modelers pick this up and explore the energy balance of Uranus with a slightly modified temperature profile. My future work includes finishing up these observations, and I'm really excited to process the observation I made just last month. And then I can start to ask some questions such as, are they consistent with trends in ground-based photometry, the trends in the stellar occultation temperatures? Here is some long-term disk-integrated photometry taken from the ground, and you can see variations that differ from expected seasonal variations. In addition, interestingly, the ionosphere of Uranus has been reported to have been cooling significantly for the past few decades. Does that translate into the lower thermosphere, upper stratosphere? It's an open question. And then I'd like to explore, as I mentioned, if there are diurnal trends, if there are latitudinal variations, seasonal, and so on. And then reprocess the Neptune data in a similar fashion. So that's where I will leave things for today. Thank you so much for your time, and I'm happy to answer your questions.
All right, thanks so much, Will. I wish there was there is an emoji for the clapping icon, right? There we go. All right, yeah, great. Thank you so much. That was an incredible presentation. I really appreciated the background. I think a lot of times that kind of thing can be skipped over, but certainly with something that some of us might be unfamiliar with, like stellar occultations, it was really helpful to have that sort of, that 101 to stellar occultations. I really appreciated that.
Sure.
We've got a couple of questions in the chat. If people have posted questions in the chat and would like to say them out loud, like feel free to just unmute yourself or raise your hand or something like that, if you would prefer. So the first question up is Leslie Young. I saw that you turned your camera on. If you'd like to ask your question, feel free. If not, I can read it for you. It's totally up to you.
You can guess that I might have many questions.
Sure.
So I'll start with the one. First of all, great talk, and
Thank you.
Good to meet you virtually. I work a lot with Mike Person and Dick French, so happy to have a third on that team. Congratulations on the October 7. I know what a feeling it is to get something like that in your pocket. What was the K magnitude of the star? How many seconds or fractions of a second between images? And if you happen to know the skyplane velocity, how quickly the star was moving relative to Uranus?
Yeah, I'll go back. Let's see if I can find that slide. So the K magnitude was something like 12. The speed was about 18 kilometers per second. And the light curve I have here is using IRTF guide dog at 3-second exposure. So yeah, I have the Morris data as well, which we did at a 1/4 second exposure, hoping for a ring occultation. Sadly, just the planet is so bright in the R band. I think we used Z. It's just there's really no hope. But in this, at least, we can see the occultation, though at 3 seconds, there's almost no chance we'll see the rings.
All right, thanks. And then it looks like Marshall Stasinski has a question in the chat, but I saw that you put your camera on, so please feel free to ask your question.
Hi, I'm Marshall Stasinski. I'm a postdoc at JPL. And my question was just about the diurnal variations. You mentioned it, and it seemed like something that would be challenging considering you really just get an ingress and an egress for a star. Is that something where you'll just need to do a whole lot of observations, or just what will it look like to try and study the diurnal variations and their impact on the observations?
Hi, Marshall. Nice to meet you. Yeah, it's a great question. And one of the fun things about Uranus is because we're so close to the sun comparatively, all of our occultations occur just before or after sunrise or sunset. And in this geometry, you can see it well, right? Because the terminator is nearly along the equator of Uranus, because we're getting near the solstice. I can't remember if it's northern or southern hemisphere. So it's interesting that like a lot of the occultations historically around the time of Voyager all occur near the equator. So we can actually compare latitudes fairly well. And what I'm curious to see, and I'll go back to the slide where I have it. Nope, not that one. Let me go back a little bit here. This one. So what I'm curious to see here is you can see there is sort of like two groups of results here. The ones that have the very strong temperature turnover here, and then ones with a fairly weak sort of a maximum. And the weak ones are all, well, mostly the dashed lines, while the strong ones are mostly the solid lines. So I don't think that's a coincidence. I think it's likely that all of these ingresses occurred around the same local time and all of the egresses occurred around the same local time. So that's something that I want to explore once I have more of a data set. And I can, in fact, do some simulations and see if that would be expected. So it's possible we're looking at something, a diurnal variation right near the terminator.
Thanks.
Hi, Will. Just since you're on this slide, this is Rick Cosentino from Space Telescope. I was going to ask you, is there any latitudinal sampling here that causes these differences? Like where on the limb are those occultation curves sounding exactly?
Yeah, nice to meet you, Rick. Thanks for the question. I mean, if you look at the dates of these, right, I chose them for a reason. And that's because all of these are sort of in the same epoch as the Voyager observations. They're all actually near solstice. So in fact, almost all of these are near the equator, plus or minus something like 15 degrees, which is kind of a lovely thing for Uranus that we get to do that comparison. And since we're going back to solstice now, I can actually compare latitudinally my data from a month ago to these ones from decades ago.
Very cool. Interesting.
All right, I have a quick question similar to that. So, you just mentioned that the reason that these specific observations were chosen were because they coincide with Voyager, but is there anything that can sort of be done here on Earth to sort of, make like a citizen science type of efforts? I know that there are currently efforts, of course, for citizen scientists to assist with occultations, but I'm wondering, what would you need going forward? Is it a matter of just getting more observations, getting more people involved and getting those observations? Is it like Leslie was mentioning, a higher cadence of images that you would need? I guess like going forward, what would you need as sort of a next step?
Yeah, it's a great question. So, I mean, these events don't happen all that often. There's something like a Uranus event, maybe every year or every other year, if we're lucky, 2 in a year, but they tend, I mean, we're talking about maybe 14th magnitude invisible. So a good event, might not come around all that often. And when it does, you just want to get the largest observatories you possibly can. The problem is there are many great stellar occultation things you can do with small scale telescopes spread out across the globe, like searching for detections of minor planets, KBOs, all those sorts of things are great with that because all you're looking for is a detection and maybe an occultation chord. In terms of being able to get atmosphere, you are going to need a little bit larger of an aperture and faster equipment than what is possible from most citizen science campaigns. So in fact, you mentioned my most recent paper was a concept study for a low Earth orbit spacecraft to observe stellar occultations where we would not be limited by atmospheric scintillation. And this is an idea that is being explored by a group at Langley. And it would, well, there are a lot of things that would be improved from that method. The downside is you have to go a lot smaller in aperture. But for the best events, once you get above the atmosphere, you can really win. So that's something that I think I'm excited about exploring a little more.
Thank you. Yeah, Leslie, you got your hand up. Go for it. It's all yours.
Thanks. If you can go back, so that I'm going to make this all about me for just 1 second. If you can go back to one of the plots that shows the 1998 occultation from
Sure.
Young et al. 2001.
Let's see.
Yes, that'll do. So it looks like you're plotting it at half-light, and this is a reminder, what you were showing, this is exactly what you were showing, that the upper boundary condition can affect your measurement of your temperature, that it takes a while before the temperatures converge and settle down. And we did some nice simulations based on Dick French's error propagation paper, I think of 78, which said he looked at an ideal isothermal atmosphere and said the best place to report a temperature is 2.5 scale heights below half-light, because that's where you're least sensitive to errors in the gradient of the upper boundary. We actually took the Voyager profile and moved it up and down in pressure. We used the Stevens et al. Compromise temperature, and we found that with a more realistic atmosphere, we got the same result. So our pressures are really at about 30 microbars. So if you move the light blue lines down to about 30 microbars, we really are in line with the purple and the blue and the orange. So
let me see if I can draw this over top so everyone can see. You're saying that I should have plotted those blue crosses like here.
Exactly.
Okay. Yeah, perhaps that's not something I fully understood in reading your paper, and it'd be great to have a chat about that.
I would,
go ahead.
I would love to have a chat. Do you have my contact info?
Yes.
Okay, great. Let's set up a time.
Excellent. Thanks so much.
I think it's probably too esoteric for this call. I would love to chat with you with what new error propagation methods you're using. I am still sticking with a combination of the French 78 theoretical and doing Monte Carlo. If you've got something smarter than that, the world needs to know.
It's not my creation. I'm using the Elliott 2003 paper.
Oh, okay. Very good.
It solves all the covariance matrices and so on.
Right.
There's also, yeah, I mean, like you mentioned, the Monte Carlo, there's a bootstrapping approach that can be done if you have a forward model. So that's something I'm exploring as well.
It's so tricky to represent the errors because as you showed, as you explained so well, it's not just the pressure at the closest approach point. Each point depends on the entire atmosphere above you. So how do you show the difference between your random errors and the correlation between the temperatures that you're showing above? It's a very hard problem.
Absolutely. And one of the suggestions that Bruno Siccardi made to me was to represent a family of inversion results by choosing slight variations in the boundary condition to show how sensitive the results are. And that is something I've looked at. I didn't show it on here because the results are not significant at this stage, but it is, yeah, it's a nice way of visualizing perhaps the different results you can get from slightly tweaking the boundary condition.
Bruno's a very smart man.
All right. Yeah. Any other questions? You can raise your hand. You can open your mic, post it in chat. I see there's a comment saying how stoked Jessica is to see uncommon stats analytic tests like AD tests being used in more research. The more we know about our data, the better our science will be. Definitely agree. I think I agree that I haven't seen a lot of those types of analyses on data sets, and I think finding the hidden information in data is of course going to be important moving forward. Definitely. Yeah. Any other questions? I usually have a slide at the very end of these with like community news, things to look out for, maybe, jobs or meetings that are coming up. Like I mentioned, I was on travel last week and I actually just got back last night at like 10:30. So I didn't have a ton of time to prepare that. So I don't have a community news slide for you all. I'm so sorry. But if you have something like a job or a meeting that you want to advertise, please send it to me. I think my contact information should be on the website, and I would be happy to forward it along to the listserv. Like I mentioned, the listserv reaches something like 230 to 240 people. So you'll definitely be getting, a large chunk of folks seeing your job ad or your meeting or any other, news that you would like to sort of distribute. I'd be happy to kind of forward it along to that listserv. And yeah, and if there are no other questions, I just want to thank you again, Will. That was an incredible talk. I really appreciated it.
Thank you.
Loved the background information, and it's exciting. Like Leslie said, it's exciting to see, any occultation because they're so, few and far between. And so, and of course, good luck to you, in your postdoc hunt. And yeah, Leslie, see your hand is raised.
Yes, so community news, just on November 4th, Dick French published or submitted rather the big paper on Uranus ring occultations 77 to 2006. So I do not know if he put it on archive.
Yeah, I was just going to ask if you have a link. Where was it published?
It was submitted to Icarus last week.
Okay, good.
I guess I'll if I hear rousing yeses here, then I'll tell him that the public has spoken, and he must cross-post to archive.
Definitely. Yeah.
Okay.
And if he wants to share those results at a future Ice Giant System seminar series, we'd love to hear from him. Definitely.
Good. He also has in draft a prediction, Uranus, Neptune, Jupiter, Saturn.
Okay.
So good. I'll try to drag him in.
Awesome. Yeah, and of course, if anyone else here would like to present at a future Ice Giant System seminar series, we're always looking for speakers. I think we're looking currently for February, March, and then onward. So absolutely reach out to me if you're interested, and we can kind of hook you up. And it's a great way to sort of advertise your work, of course, maybe look for jobs, and then also just keep in touch with the community. A whole part of this seminar series is to keep in touch with this Ice Giant Systems community, and that's going to be especially important with JWST online, with the Uranus orbiter and probe hopefully coming on soon. This is going to be a big community, and things are going to be happening fast, and I'm excited for it. So if there isn't anything else, I'll thank Will one more time, and good luck to you. And I'll close this Zoom room. So yeah, thank you so much, Will.
Thank you, Jody. This was a blast.
All righty. Bye, everyone. I'll close this Zoom room up.
Thanks, everyone, for attending.